Now let's try to code in MATLAB for the continuous function fx equals to 1, this constant function, using generalized Fourier series. So we have derived that our fx is equals to n from 1 to infinity 4 over n pi sine n pi x over L, where this n is only odd number, 1, 3, 5, 7. And remember, our fx was equals to 1 when we derive this generalized Fourier series to represent fx. And the orthogonal basis sites are from the Sturm-Liouville problem, which minus y double prime equals to 4 y. And we have our boundary conditions y0 equals to 0, y L equals to 0. So when we derive this general Fourier series expansion to represent fx equals to 1, beside this x is indeed in between the 0 to L, but the only thing didn't satisfy is that this fx is now satisfied for these boundary conditions. Let's see how the MATLAB behave for this derived general Fourier series expansion to represent this fx, even though the fx is not fit for the boundary conditions. Okay, so let's see the MATLAB. Okay, you can see the screen. This is the script. Using generalized Fourier series to represent the fx function equals to 1. The goal here is trying to evaluate the infinite series expansion for fx equals to 1 in terms of a sine cosine series, which is the Fourier series expansion. For this problem, we already say that the Bn is equals to 4 over n pi, okay? And the function, the orthogonal basis set is sine n pi x over L, where this n is only the odd number, so it's 2n minus 1, where the m equals to 2n minus 1 to represent only odd number. And now let's try to see how we can code this part. As per usual, we will clear out, close all for the other results running on the command. And let's start our figures from 0. We will set our domain. Let's say our domain should be from 0 to L. Let's set a number for L, where the L equals to 3. Of course, you can set up any other numbers. This L is very user-defined. I just define L equals to 3. And the X is the independent variables in between 0 to L. And let's have the subdomain is very small subdomain. So in between the 0 to L, you will have 200 dots in between. We define C over 4, C is equals to 4 over pi. Remember, our constant Bn should be 4 over n pi, so we just derive, we just set up 4 over pi here, which is when the n is equals to 1, so C is 4 over pi. The first term for our sum of the general Fourier series should be 4 over pi sine pi x over L when n equals 1, right? So that is our first term in the sum part. We also trying to set up, this is our sum. So the S5 means we only sum 5 terms. So it's sum of 5 terms equals to the first partial sum. That just give a value for your sum term. Then when you're doing the loop, you will keep adding the more terms into your sum part. So we will calculate different number of the sum, trying to see how the behavior is related to the number of the terms involved into the sum. we will calculate 5-term, 20-term, and 50-term, trying to see how it's compared to each other. So when the sum term include 5-term, then you basically involve 5 different even number of your n. So the m is represented by the even number of n, so it's 2n minus 1. The sum 5 is updated whenever you run one loop, and that is basically the sum of the Fourier series, which is 4 over n pi times sine n pi x over L. And you can end when you finish running these 5 terms. We also can calculate 20 terms, 50 term, all the same. The only difference is that you just involve more terms into your sum to represent your continuous function fx. And after you getting all the sum number, you can plot the curve. You can plot compare to each other term. So that you can see when you include last term of the Fourier series, what is the fx function look like. When you involve more terms, what is the fx look like, okay? So that is the script for MATLAB. Let's run and trying to see what the plot look like. Okay, so I will share the picture. You can see this picture. This is Fourier series approximation to represent your continuous function of x equals to 1. When you include just one partial sum, basically just one sine function, it looks like the sine function from 0 to 3, right? Well, when you involve 5 terms, you can see this oscillating part. And you can see that it's more close to the function fx equals to 1. And if you see the downside picture, which you involve more terms, like 20th term, which is represented by the blue color, 50th term represented by the red color, you can see that as you involve more terms of the sine function, the Fourier series function, you will be more close to the true function where the fx equals to 1 for here. And you also notice that for the boundary 0 and 3, they didn't fit well, right? It didn't fit well because this fx equals 1 itself didn't satisfy for the boundary conditions. That's why we have very big noisy near the boundary site. But overall, it can represent this continuous function fx equals 1 using generalized Fourier series expansion.